When considering types of experimental error, it's first useful to know what we mean by error. And an error is something that causes a difference between a measured or calculated value and the true value. And we can talk about experimental error in two categories. Let's use a little Venn diagram to show this. The first type of error we like to consider is random error. And the second type is systematic error. And we need to know the difference between these two types of error, and also we need to be able to give examples. Let's start with random error. So a random error can cause a measured value to be too low or too high with an approximately equal probability. Let's see if we can apply this to some examples. The first example here is always present when making measurements, and that's limitations in the measurement equipment itself. This is known as uncertainty, and if you're not quite sure what this term means, you might want to check out the separate video that runs through that. Put simply, all experimental measurements we make are recorded with an uncertainty or a plus or minus to show a small range in which we are confident that our measured value falls. And given that uncertainty always is this plus or minus sign, the measurements could be too high or too low, and this is totally unavoidable given the precision in our equipment. The only thing we can do to reduce the range of uncertainty in our measurement is use more precise equipment. A second example of random error might be changes in the surroundings during an experiment. For example, if I was investigating the breakdown of vitamin C in orange juice at say 25 degrees or room temperature, I might expect that in my lab there will be natural temperature fluctuations. Maybe there's a window open, or maybe the weather outside is changing. And this might mean that sometimes my temperature is slightly higher than 25 degrees, and other times it might be slightly lower. It's also worth mentioning that this kind of random error can actually be controlled. Perhaps using a water bath set at 25 degrees might be a better way to do it, and will reduce the impact of that random error. A third common example might be misinterpreted measurements made by myself or the people in my group during the experiment. For example, I might be recording the time taken for a colour change to occur in a solution. And if different people in my group are recording these times, they might judge this colour change at slightly different points. Again, we consider this a random error because some people might judge the point too early, some people perhaps too late, so my time can variate above and below the true value. This is probably controllable by, for example, making the same person judge that colour change each time. A final example might be a lack of sufficient data collection. Because random error causes values to be too high or too low with approximately equal probability, by repeating a measurement and using those repeat measurements to take an average, I can actually reduce the impact of random error. And this means that without enough measurements or repeat measurements, I am unable to minimize the random error present in my average. So in IB experiments, we should always make sure to repeat a measurement at least 3 times. Let's now have a look at systematic error and consider how that's different. Unlike the variation that we see in random errors, a systematic error will always cause a measurement to be too high, or it will always cause it to be too low. Let's have a look at some examples. The first common one when measuring volumes is reading the volume from the top of the meniscus instead of the bottom of the meniscus, which is where we should be doing it. If I always take my measurements from the top of the meniscus, the volumes that I record are always going to be too high. And because they're always wrong in one direction, we call it a systematic error. A second common systematic error when measuring the volume of a gas is perhaps a leak in the equipment causing a loss of gas. In this case, a gas leak will mean that my measured volume of the gas is always lower than it should be. So again, this is considered a systematic error. Another systematic error might be overshooting the endpoint in a titration. If the target colour change in my titration is from colourless to a pale pink colour, and I notice each time that I'm getting quite an intense pink colour, then it looks like I'm adding too much from my burette in each case. So the volume of titrant that I'm adding is always too high and therefore is a source of systematic error. The final example we'll look at is the use of a balance that is not zeroed or tared correctly. In the balance I've drawn on the right, you can see that it's starting off at 0.01 grams, so any masses I record on this balance will be slightly too high by 0.01 grams each time. Again, this would be considered a systematic error. Let's now summarise the key points from this video. Firstly, a random error can cause a measured value to be too high or too low with approximately equal probability. We can minimise the impact of random error by repeating measurements and calculating averages. Systematic error always causes a measurement to be too high or always too low. In order to minimise the impact of systematic error, we need to carefully consider our experimental design and procedures we use before we do the experiment. And finally, as a note for exams and the internal assessment, you'll be expected to identify sources of error and might be asked to suggest improvements. Hopefully, this video is of some help.